Hi Pre-Calc students, this is Mrs. Mueller and this is 6.2 dimensional analysis. Dimensional analysis is a fancy phrase for converting between units. So we're going to be working with some different rates, some angular, some linear, and converting them into other things. So this slide right here, you might not want to write this down. It's just to give you an idea of what to expect here, kind of the direction we're heading into. So it says a bike tire has a radius of 24.5 inches. It is rotating at 150 revolutions per minute. How fast is the biker traveling in miles per hour? So people use this when they're creating programs that tell you how fast the bike goes, like a speedometer. It doesn't just go off of magic. It goes off of kind of converting the revolutions into a linear distance and then divides it by time so we can figure out how fast we're going. So we're going to kind of break things down and then work our way up to problems like this one. So this slide here, you'll definitely want to write this down. These are some helpful conversions that we're going to be using throughout this lesson. The first one I think is one that's pretty obvious and one that we've used quite a bit. One revolution, one trip around the circle is 360 degrees. So that's just that's an angular conversion. One revolution is the same as 360 degrees. Okay. Another one that's maybe a little bit less familiar, but we've been talking about it a little bit, is the fact that around a circle is 2 pi radians. So 360 degrees, 2 pi radians, they're the same thing. Therefore, one revolution would be the same as 2 pi radians. And remember, radians are just another way to measure angles. Okay. Third one, this one we are going to use anytime we're going between angles and linear distances. So like, if we're going from inches and feet, things like that, into angles or working with revolutions, we're going to use this one that says that one revolution is equal to the circumference of your circle. So if you're talking about a bike tire or a car tire or a Ferris wheel or something like that, the linear distance it travels is equal to its circumference, which is 2 times pi times radius, or sometimes you will see it just as pi times diameter. Okay, same thing. Circumference is 2 pi r, or just pi times diameter. And that linear distance, that's something that's going to be measured in, like I said, inches or feet or miles, or some sort of length that we are used to seeing, meters, things like that. So that one is important when you are switching between linear distances and angular distances. I wish I would have made these the right color. Let's make that one red. And this one blue, so they match. Yes, so use when you are changing from linear into angular or from angular into linear, either direction there. And you'll see what I mean there when we work through some examples. All right, so a couple other things that are going to be important here. Linear velocity. What does linear velocity mean? It's the rate of change along a straight path. So linear, you think of line, lines are straight. Rate of change along a straight path. So in this situation, we're going to be thinking about things like maybe feet per minute, or maybe meters per hour. Or one third example here, maybe miles per hour. That's one that we use quite a bit in this country. Okay, so each of those are rates. They're ratios, and all of those things on the top and then in the numerator are all things that we measure, linear things in lines, feet, meters, miles, things like that. On the bottom, we have different examples of time, minutes, hours. We could have seconds down there as well. Okay, angular velocity. Angular velocity is the rate of change of an angle. So, for example, we might have like 25 degrees per minute. Okay, something is changing at a rate of 25 degrees per minute. Or maybe 4 pi radians. And radians can be abbreviated RAD. Maybe 4 pi radians per second. Or maybe 3 revolutions per day. Okay, each of those numerators are all different ways to talk about angles. 25 degrees, 4 pi radians, 3 revolutions. So we could either do 3 times 360 degrees, or we can do 3 times 2 pi radians, or we can just leave it as revolutions. But each of those are ways of measuring angles. Okay? All right, now we are going to dive into our first example. And we are starting with 2 revolutions per minute. And the goal is to end up in degrees per second. So we are, we're converting revolutions per minute into degrees per second. So I like to think about it as like, what do we need to get rid of here? So in terms of our time, we're currently in minutes and we need to get into seconds. So we need to get rid of minutes and we need those minutes to become seconds. Well, if you want to get rid of something, and currently our something that we're talking about is in the denominator. It's on the bottom. We want to get rid of this minutes on the bottom. That means that we need to put a minutes on the top so that we can cancel it out. Okay? And we want to get into seconds. Well, we can do that all in one step. Okay? I know how many seconds are in a minute. I know that there are 60 seconds in 1 minute. So I can just set up a new ratio like that. It's called a conversion factor. And we can convert our minutes into seconds just like that. And when I'm doing these, I like to cross things off as I go so that I know that I'm done with it. So I'm going to cross off the minutes. So I now know that my answer is going to be in seconds. I'm not going to get rid of the seconds. I'm going to keep them there because that's what our answer needs to be in. Okay? Now the other problem is that we want our answer to be in degrees, but we are currently in revolutions. So we need to get rid of revolutions. To get rid of revolutions, if they're currently on the top, we need to put them on the bottom. Okay, so revolutions, one on top, one on bottom, we can get rid of them. We want our final answer to be in degrees. So I'm going to put degrees there. Now the question is, how many degrees are in a revolution? What's the conversion factor there? What's something that's equivalent to each other that we can put in there? Well, from our very first slide, or maybe our second slide, we kind of reminded ourselves that there are 360 degrees in 1 revolution. Those two things are equivalent, so we can put them together in a new ratio. What that allows us to do is it allows us to cross off revolutions on top and on bottom, and then we can just double check to make sure that what we have left is what we want left. So we are left with degrees. Good. We want degrees on top. We want seconds on the bottom. Check. We got it. Okay. Now all we have to do is multiply straight across the top. So 2 times 1 is 2 times 360 is 720. And on bottom, we have, that was nothing, or just 1. And then we have 60 times 1. So we just have 60 on the bottom. So we have 720 degrees over 60 seconds. Now that's kind of weird. I would rather not have a fraction that looks like that. So we should grab our calculator and let's see if we get a nice answer to begin with. So let's do 720 divided by 60. 720 divided by 60. And we end up with 12, which is nice. So we actually end up with 12 degrees per second. We should write our final answers like that. 12 degrees per 1 second, or just per second. All right, example 2. And these ones are kind of nice because it tells you how many steps there are. So this time we're going to have 3 different conversion factors to get from where we're starting, which is 100 pi radians per hour into revolutions per second. Okay? So I don't know, I kind of tend to do time first. You certainly don't need to. but I usually like to work with hours and minutes and seconds first just to get myself going. So I know that we're starting in hours and we need to get to seconds. So what I would do here is I want to get rid of hours, but I maybe wouldn't jump all the way to seconds. I would maybe convert that one into minutes first. So 1 hour is 60 minutes. Now we can get rid of our hours. And then we want to get rid of minutes. So we want minutes on top now and seconds on the bottom. That will allow us to get rid of our minutes and end up in seconds, which is what we ultimately want. So there are 60 seconds in 1 minute. Okay, and now here's our seconds, which is what we want. So we're good with time. Now we have to go back and deal with our radians here. So this is an angular one. So we're beginning in angular, we're ending in angular. Radians are angles, revolutions are angles. So that's good. We're not switching between linear and angular. We're going from angular to angular. So the question is, we want to get rid of radians. So we want radians to be on the bottom. We want to get rid of them. And we want revolutions to be left on top. So the question is, how many radians are in a revolution? Well, that was again from that first slide. There are 2 pi radians in 1 revolution. Okay. Now something else nice happens here. So we can get rid of radians and we can get rid of radians. We can also get rid of this pi. We have a pi on top and a pi on bottom. So we can just clear that out and not have to worry about it anymore, which is kind of nice. Okay. At that point, double check that you have what you want. We have seconds on the bottom. That's the only thing that didn't cross off. We have revolutions on the top. That's the only thing that didn't cross off, and that's what we want. We want revolutions per second. Now all we do is multiply across the top. 100 times 1 times 1 times 1 is just 100. And then on the bottom, we have 60 times 60 times 2, which ends up being 7,200. 60 times 60 times 2 is 7,200. Now again, we don't really want to leave it like that. So what we can do is either reduce the fraction, but that gets kind of weird. That would end up with like 1 revolution per 72 seconds, which that'd be kind of a weird way to answer that question. So I would just, again, grab a calculator, type that in, 100 divided by 7,200. And you end up with, I think it's going to say round to the nearest tenth, but that would be kind of weird. On your worksheet it says that. That'd be kind of weird in this situation. So let's just go like 0.014, just to get an idea of what our answer actually is. So 0.014 revolutions per second. Moving on to the next example. So this is where things start to get a little bit trickier. So it looks like we are starting in revolutions, which is angular, and we are ending in feet, which is linear. So when that happens, anytime you are asked to convert from angular to linear or linear to angular, your brain needs to remember that at some point you need to do circumference. Okay, when you are switching, in this case, we are going from angular to linear. Okay, so let's just, I'm going to keep going the way that I normally do it, and then we'll get to that circumference piece when we're ready for it. But what I would do first is convert your time. So we're in minutes, we want to get to seconds. So we want to get rid of minutes, we want to end up in seconds. So there are 60 seconds in 1 minute. Our minutes can go away, and we're in our seconds, which is where we want to be. Okay, now we are trying to go from revolutions to feet. Okay, so what we should do is look here. So our radius, they're telling us the radius of this thing, I don't know what it is, a wheel, more than likely. The radius is 120 inches. So we want to figure out the circumference of it. So circumference is 2 times pi times radius, which is 120. Okay? And what we come up with there, and I would not even mess with rounding pi or anything like that. I would do 2 times 120 is 240. So 240 pi. And we are in inches. Be careful here. We are in inches. So the circumference of this thing is 240 pi inches. Okay, so now the question is, what the heck did we just figure out? So we gotta stop and think about that a second. The circumference is 240 pi inches. Oh, okay, so that's how far we traveled. So if you have a circle here, and the circumference of it is 240 pi inches. If we stretched that out, so if we took this and just kind of rolled it out, we would have started at 0 and we would have ended up at 240 pi inches after one single revolution. If that tire goes around one complete time, the linear distance it's going to travel is the same as its circumference. It's going to be 240 pi inches. Okay, so we're trying to get rid of revolutions. Currently it's on the top. We need to put it on the bottom. Okay, now we have a conversion factor though. One revolution is equivalent to 240 pi inches. Okay, now we're getting someplace. Now we are done with revolutions and we are in inches. So we're very close to getting to feet. We want to end up in feet. So if we want to get rid of inches, we want inches on the bottom, feet on top. There are 12 inches in 1 foot. Inches can go away, and we are left with seconds on the bottom, feet on top, which is where we want it to be. Okay. At that point, you can just kind of multiply everything across the top, everything across the bottom. Our pi is not really going to disappear this time, so let's just leave it in there. So 10 times 1 times 240 would be 2400 pi over 60 times 12, which is 720. Okay, and then you can just type that into a calculator. Once again, 2400 pi. I guess I can do that quick. 2400, you can use the pi button, divided by 720. And you're going to end up with 10.47, or I think, again, your worksheet says to round to the nearest 10, so we'll just go 10.5. So final answer, 10.5 feet per second. All right, jumping into example 4. This time we're not really given much of a setup, so it's on us to kind of do the whole process. So it says a merry-go-round is spinning at a rate of 1 revolution per second. 1 revolution per second. I would stop right there and write that down. 1 revolution per is just the division sign, 1 second. You can put the 1 there or not put the 1 there, it doesn't really matter. 1 revolution per second. Okay, our question is, how fast is it turning in degrees per minute? So when we are done here, we want to be in degrees per minute. And I don't know how many steps it's going to take, probably not many, but let's leave enough space so that we can fit in as many as we need to. Okay, so from that point, just same process. I don't want seconds, I want minutes. So I'm going to get rid of seconds, put them on top. I want to keep minutes, put them on the bottom. So I know that there are 60 seconds in 1 minute. Seconds can go away. We're left with minutes, which is where we want to be. Okay. Now revolutions to degrees. That's actually not going to be super difficult. I want to get rid of revolutions, so they stay on the bottom. I want to end up in degrees. So the question is, how many degrees in a revolution? 360 in 1 revolution. And both of these are angular. We started in angular, revolutions are angular. We're finishing in degrees, which are angular. So we don't need to do anything with circumference. Okay, so I think we're going to be good there. The two things that we have left that aren't crossed off are degrees and minutes, which is good. So we want to multiply straight across the top. 60 times 360 is 21,600. And then across the bottom, we just have 1 times 1 times 1, which is 1, so we're done. 21,600 degrees per minute is our final answer. All right, example 5. If a tire on a race car is traveling at a rate of 1,500 revolutions per minute. So again, I'm going to stop there and just write that down. 1,500 revolutions per 1 minute. Okay, and the tire's diameter is 32 inches. Okay, I'm assuming we're going to need that. So diameter is 32 inches. I'm just going to jot that down. Determine the car's speed in miles per hour. Okay, so we want to finish here, miles per hour. So miles per hour. All right, so let's think about what we're doing here. We're starting with revolutions, which is angular. We are finishing in miles, which is linear. You measure miles by, measuring a straight line. Okay. One more thing we might need here is that a mile is 1 mile is 5,280 feet. I don't know if you know that or not, but I have a feeling that we're going to need that. Okay. So if we're going from angular to linear, we definitely need to find the circumference. So I'm just going to do that right away. We're going to need it, so let's do it. So circumference is 2 times pi times radius, or in this case, just pi times diameter is going to be easier. They give us the diameter. So pi times 32, or let's just leave it as 32 pi. And that is in inches. That's important. Now, I'm going to do time first. I'm just going to keep doing that the same way. So I don't want minutes, I want hours. So I want minutes on top. I want hours on the bottom. There are, 60 minutes in 1 hour? So minutes can go away, we're in hours. We're good there. Now we need to deal with our revolutions. Okay, our revolutions and our circumference kind of correspond to each other. So we want to get rid of revolutions. So they go on the bottom. 1 revolution in this case is equal to our circumference. They're the same thing. A revolution and a circumference are the same thing. That's how we convert from angular into linear. So that's where I want to put our 32 pi inches on the top. Now we can get rid of revolutions on the top and bottom. And we're getting kind of close. We're in inches per hour right now. We want miles per hour. So the first thing I would want to do is maybe slide this down so it's not in our way. It's getting longer than we thought. We want to get our inches into feet. I don't want to go right from inches to miles. That's too big of a step for my head. So there are 12 inches in 1 foot. And then there are, like I said, 5,280 feet in 1 mile. So inches and inches go away, feet and feet go away, and we are left with miles on top, hours on the bottom. That's a good thing. Okay. Now we can throw our equal sign in and start multiplying. So on top, we would do 1,500 times 60 times 32 pi. On the bottom, we would do 1 times 1 times 1 times 12 times 5,280. We can type that into a calculator. I won't bore you with that. And we will end up with 142.7 miles per hour. Or you could write that too, like that. That's usually how we actually write it. mph, miles per hour. That's usually how you will see that. All right, and last example here, example 6. Joe's running on a circular track with a diameter of 1,000 feet. I'm assuming we're going to need that, but let's keep reading. If you can run at a constant speed of 4 feet per second, what is Joe's rate in radians per hour? Okay, so we're finishing here. We want to finish in radians per hour. That's where we want to finish. Where are we starting here? Well, I guess we probably want to start with the other rate they're giving us. They're giving us a rate of 4 feet per second. So 4 feet per second, or per 1 second. You can add that in if you want. Okay. Now we got to start with that radius, probably, or the diameter. I guess they gave us. They gave us the diameter of the circular track. So let's figure out what the circumference of the track is. The circumference of the track is pi times diameter, so pi times 1,000, or 1,000 pi, and that is in feet. Okay, so we're going to need that at some point. I'm not going to start with that. I'm going to start with our time. So I want seconds to be hours. So I would maybe do 60 seconds in 1 minute. And then I would maybe do 60 minutes in 1 hour. So we can see our seconds can go away, our minutes can go away, and we're left with hours, which is where we want to be. Okay, now we started out in feet. We don't want to end up in feet. We want to end up in radians. So if feet were on the top, feet now need to go on the bottom, and that's where this comes into play. Okay. So we want 1,000 pi feet on the bottom. That is equal to 1 revolution. Not 1 radian. We're not quite there yet, but 1 revolution. Because that's the track. So 1 time around the track is 1,000 pi feet. So our last step, so we're done with feet. They're gone. Currently we're in revolutions. We want to end up in radians. So revolution on the bottom, radians on top. There are 2 pi radians in 1 trip around the circle, in 1 revolution. So that's where we can get rid of our revolutions. Okay. So on top, I can go ahead with this one, I guess. We want to do 4 times 60 times 60 times 2 pi. 4 times 60 times 60 times 2, and I'm going to leave the pi out, and I'm going to say 28,800 pi. Over, equal sign here, over at the bottom, which is just 1 times 1 times 1 times 1,000 pi. So really, we just end up with 1,000 pi. And we actually could have done this sooner if we would have realized it. I guess I just didn't realize it right away. There's a pi on the top and a pi on the bottom. So we can actually just cancel those guys off. And we are left with 28,800 divided by 1,000, which ends up being about 28.8 radians per hour. All right, so that's about as complex as they come. So if that would make sense to you, you're probably going to be okay with this stuff.